This video looks at the work on continuous random variables for Unit 2 of the WJEC Further Maths specification. The specification says that we have got to be able to use probability density functions and cumulative distribution functions to describe continuous random variables. We need to be able to use these things to find the medians, quartiles and percentiles of a random variable, and also to find the mean, the variance and the standard deviation of these random variables. And we should also be able to find the expected value of a function of a continuous random variable. So, in terms of key facts, continuous random variable is a random variable that can take values over a whole interval of numbers. Continuous random variable that takes values over an interval can be described using either a probability density function, and we usually use a little letter for the probability density function, or the random variable can be described by a cumulative distribution function, and for the cumulative distribution function we usually use a capital letter for the function. The probability density function is rather similar to the idea of a histogram in statistics, whilst the cumulative distribution function is similar to the idea of a cumulative frequency diagram in statistics. So for a probability density function, little f of x, the function must be greater than or equal to 0 for all values of x. The total area between the x-axis and the curve must be equal to 1. And areas under part of the curve correspond to probabilities of the random variable x. And notice that it really doesn't matter whether the interval that we're trying to find the probability for is a closed interval or an open interval or half closed and half empty and half open. So the probability that the random variable x lies between alpha and beta is given by the integral between alpha and beta of the probability density function. And it doesn't matter whether the inequality involved is alpha is less than x is less than beta, or alpha is less than x is less than or equal to beta, or alpha is less than or equal to x is less than beta, or alpha is less than or equal to x, which is less than or equal to beta. All of those probabilities are given by the integral between alpha and beta of f of x dx. The cumulative distribution function, f of x, is such that f of x is the probability that the random variable is less than or equal to little x. If we know the distribution function, then it is easy to work out probabilities, since the probability that x lies between alpha and beta will simply be f of beta minus f of alpha. The probability density function, little f of x, is the derivative of the cumulative distribution function, and the cumulative distribution function is the integral between minus infinity and x of f of x dx. So in other words, to find the probability density function from the cumulative distribution function, we must differentiate. To find the cumulative distribution function from the probability density function, we must integrate. If we have a continuous random variable x with a probability density function little f of x, then the mean is obtained by integrating x times f of x, and the mean is the same thing as the expected value of x. The variance is found by integrating x squared times f of x dx between the appropriate limits, and then subtracting the mean squared. And the standard deviation, as always, is just the square root of the variance. And as in our statistics, we can say that most of the distribution of x will lie between the mean minus 2 standard deviations and the mean plus 2 standard deviations. The expected value of a function of a random variable can be found, again, using integration. So if we've got a function g and we want to find the expected value of g of the random variable x, then we need to integrate g of x times by the probability density function f of x between the appropriate limits. And this means that we can again write the variance of x as being the expected value of x squared, take away the mean squared, in other words, take away e of x squared. And now we need to just consider how to find the percentiles of a continuous random variable, and this can be done using either the probability density function or the cumulative distribution function. So if we've got a continuous random variable x, taking values on the interval starting at a, ending up at b, then the nth percentile is either the solution of the equation f of w, big F of w, the distribution function of w equals n over 100, or equivalently it's the value w such that the integral between a and w of the probability density function equals n over 100. And then this immediately gives us extensions to the definitions for the median, the lower quartile and the upper quartile of a continuous random variable. It's worth realizing that there's a large number of results about continuous random variables given in the formula booklet that you will be given during the course of your examination. The information about the exponential distribution will be considered in the next video in the series. So let's now have a look at some examples. For the first example, we've got a machine which is designed to cut wooden poles to a length of 200 centimeters. The actual length of the poles cut by the machine is actually 200 plus x centimeters, where x is a continuous random variable whose cumulative distribution function, f of x, is given by f of x equals 3/16 of x times by 4 minus x for values of x between 0 and 2. If x is less than 0, f of x is 0, and if x is bigger than 2, then f of x is 1. So the first thing we're being asked to do is we're being asked to find the probability that a randomly chosen pole cut by this machine has a length between 200.6 and 201.4 centimetres. Now, if the length lies between 200.6 and 201.4, that means the random variable x must lie between 0.6 and 1.4. Now, we commented earlier that it really makes no difference at all whether we deal with less than inequalities or less than or equal to inequalities. So we can move between the two without it making any difference at all to the final answer. Probability that x lies between 0.6 and 1.4 is the same thing as the probability that x is less than 1.4. Take away the probability that x is less than 0.6. In other words, if we remember that the probability that x is less than something is precisely what we mean by the distribution function. Sorry, the cumulative distribution function of the random variable. Then we have got the probability that x is less than 1.4 is f of 1.4, and the probability that x is less than or equal to 0.6 is just f of 0.6. Inserting 1.4 into the rule for f of x, we get 0.6825. Inserting 0.6 into the rule for f of x, we get 0.3825. So the required probability is 0.3. Moving on, part B asks us to find the probability density function for x and hence obtain the mean and variance of x. Well, we need to remember that we have two functions, the probability density function and the cumulative distribution function, that to move from the probability density function to the cumulative distribution function, we have to integrate, and to move from the cumulative distribution function back to the probability density function, we've got to do a differentiation. If we look at the distribution function, we can see at the moment we've got f of x is 3/16 x times 4 minus x. That of course multiplies out to 3/4 x minus 3/16 x squared. So it's now relatively easy to find the probability density function for x. We need to say that the probability density function for x, that's little f of x, is the derivative of the distribution function for x, and the derivative is 3/4 minus 3/8 x for values of x which lie between 0 and 2. If x is less than 0, then the distribution function is 0. If we differentiate 0, we get nothing. If x is greater than 2, the distribution function is just equal to 1, and if we differentiate 1, we just get 0 again. So we can say that the probability density function is 3/4 x minus 3/8 x if x lies between 0 and 2, and it's equal to 0 otherwise. So we've found the probability density function. We can now move on and calculate the mean, or the expected value of x. And we know that to find the expected value of x, we've got to integrate x times f of x between the appropriate limits. So in this case, we've got to integrate between 0 and 2, because the random variable only takes values between 0 and 2. And we have to integrate x times by the probability density function, which is 3/4 minus 3/8 x. So multiplying the brackets out, first of all, and then integrating, we've got 3/8 x squared minus the 1/8 x cubed as the result of the integration. But we need the value of that when x equals 2. Take away the value of that when x equals 0. When x equals 2, 3/8 x squared minus an 8th x cubed is 12/8. Take away 8/8. And when x equals 0, the value of 3/8 x squared, take away an 8th x cubed is just 0 minus 0. So it doesn't give us anything at all. So we're ending up with the expected value of x is 1/2. Similarly, for the variance of x, we know that the variance of x is the integral of x squared times the probability density function. Take away the mean squared. So that's the integral between 0 and 2 of x squared times 3/4 minus 3/8 x. That's the probability density function. Take away the mean squared, which is take away 1/2 squared. We've just found the mean on the previous page. So going through the integration details, multiply the brackets out. Now perform the integration and evaluate when x equals 2 and when x equals 0 is going to give me 2 minus 3/2 when x equals 2. When we substitute in x equals 0, we get nothing at all. So what we're ending up with is 1/2, take away 1/4, which gives me 1/4 for the variance. Okay, so we've found the mean. However, what we haven't yet, so we've now got, to find the mean and the standard deviation of the lengths of the poles produced by this machine. Well, the length of the pole is equal to 200 plus x. So the expected value of L is the expected value of 200 plus x, which is 200 plus the expected value of x. We found out that the expected value of x was 0.5, so the expected value of L is 200.5 centimeters. The variance of L is the variance of 200 plus x, and this is simply the same as the variance of x, which we found out was 1/4 or 0.25. But the question asks us for the standard deviation, not the variance. So we can now say the standard deviation of L must be the square root of 0.25, which is 0.5 centimeters. Moving on to our second example, which comes from the 2011 S2 paper. We have a continuous random variable u is uniformly distributed on the interval AB. We've got to start by writing down the probability density function of u. The fact that the random variable u is uniformly distributed on the interval AB means that the probability density function takes a constant value between A and B and is 0 everywhere outside that interval. We know that the area between a probability density function and the x-axis must equal 1. The base of that, in this case that area is a rectangle whose base is of length b minus a, so its height must be 1 divided by b minus a. So we know that the probability density function for u takes the value 1 over b minus a, if u lies between a and b, and it equals 0 otherwise. So we've now got to use that to show that the expected value of u squared is a squared plus ab plus b squared, all divided by 3. Well, we know that the expected value of u squared is the integral of u squared times f of u between the appropriate limits, which in this case are a and b, because the random variable u only takes values between a and b. So we've got the integral between a and b of u squared times by 1 over b minus a. Well, 1 over b minus a is a constant, so we can pull it outside the integral. So we've got 1 over b minus a times by the integral of u squared between b and a, sorry, between a and b. Integrating gives me a third u cubed. Putting the limits in means that I have now got 1 over b minus a times by a third b cubed minus a third a cubed. Let's pull the factor of a third out first of all. So we've got 1 over b minus a times by a third of b cubed minus a cubed. But b cubed minus a cubed factorizes as b minus a times by b squared plus ab plus a squared. Now you'll notice there we've got a term which is 1 over b minus a, but later on we've got a term which is b minus a, and they're all being multiplied together, so those two terms will cancel each other out, and we're left with b squared plus ab plus a squared, all divided by 3. Switch the order around, and we've got exactly what we were being asked to prove. So moving on to the second part of the question, we're now told that a piece of string of length 12 centimeters is cut at a random point. The length of the resulting shorter piece is denoted by x centimeters, and the length of the longer piece by y centimeters. And we're told that x is uniformly distributed over the interval 0 to 6. So there we are, there's our quick sketch of the distribution of the random variable x, the probability density function for the random variable x. We can straight away see that we have a connection with the previous part of the question, and the value of a, the lower limit of the interval, is 0, the upper limit of the interval is 6. So we can write down that the mean, or the expected value, of the random variable x is 3. We can either appeal to symmetry for that, or we can use the result about the continuous uniform distribution, which is given in the formula booklet. The variance is the expected value of x squared, take away the mean squared, and the expected value of x squared we can work out using the result from part A, using the fact that we, in this case, we've got a equals 0 and we've got b equals 6. If we simplify that, then we've got the 0 squared plus 0 times 6 plus 6 squared is 36 divided by 3, which is 12. Then we've got to take away the 3 squared, which is 9. So we're ending up with the variance is equal to 3. Now again, that result could have been obtained from using the formula given in the formula booklet. Finally, we know that the longer piece must be together with the longer piece together with the shorter piece must make 12 centimeters. So the longer piece must be 12 minus the length of the shorter piece. So we must have y equals 12 minus x. We're being asked to work out the expected value of xy, or the mean of xy. Now in this case, x and y are most certainly not independent. So it is not true that the expected value of x times y can be written down as the expected value of x times by the expected value of y. We're going to have to be a little bit more subtle about it. What we can still though say is that the expected value of x times y is the expected value of x times by 12 minus x. In other words, the expected value of 12x minus x squared, which can be split up as 12 times the expected value of x minus the expected value of x squared. Now, we have already seen that the expected value of x is 3. So we've got 12 times 3, and then we've got to take away the expected value of x squared. And the way that we've tackled this question so far, we've got the expected value of x squared is equal to 12 by the work that we've already done. So we can say the expected value of x squared is 12. So the expected value of xy is 12 times 3, take away 12, which is 24. The time t hours taken by a lorry to travel a motorway journey of 96 kilometers between two cities is to be modelled as a continuous random variable. It's suggested that the random variable has probability density function f of t, as described in the question, where k is a positive constant. First of all, we've got to find the value of k. Now it's important to remember that the area underneath a probability density function must always equal 1. So in this case, that's telling me that the integral between 1 and 3 of k over t cubed must equal 1. The k is a constant, so let's pull that outside. So we've got k times the integral between 1 and 3 of 1 over t cubed must equal 1. Integrating now gives us this. And if we insert the limits of 3 and 1 in, we obtain k times minus 1/18 minus minus a half must equal 1. In other words, 8/18 of k must equal 1, so k must be 9 over 4. So we found the value of k. Second part of the question asks us to find the probability that the next time a lorry makes this journey, its time will be greater than the expected time. So our first task is to calculate what the expected time for the lorry will be. So to calculate the expected time, we need to do the integral of t times by the probability density function. So in this case, we've got the integral between 1 and 3 of t times k over t cubed dt. The k can be pulled out. The t times 1 over t cubed simplifies to 1 over t squared. So we've got k times the integral between 1 and 3 of 1 over t squared. Integral of 1 over t squared is minus 1 over t. Insert the limits. We've got k times by minus a third minus minus 1. So in other words, we have 2/3 k, but we know that k is 9 over 4. So 2/3 of 9 over 4 is 18 over 12, or 1.5. So we know that the expected time for the journey is 1.5 hours. So what we're after now is the probability that t is greater than 1.5. So that means that we want the probability that t is more than 1.5, and it can be anything up to 3. So we want the integral, we want the area under the probability density function between 1.5 and 3. So that's the integral between 1.5 and 3 of the probability density function. So that's the integral between 1.5 and 3 of k over t cubed dt. And we've done this integration already earlier on in the question, so we can jump, we don't need to go through all the details again, we can just jump straight to the point where we say we know the k comes out of the integral and 1 over t cubed integrates to minus 1 over 2t squared. Put the limits in, and we end up with our probability of 3/8. Moving on to the next part of the question, we are asked to consider the random variable, which is the average speed in kilometers per hour of a lorry for this journey. And we're told that if t has the probability density function described in the first part of the question, then it can be shown that the average speed v has got a probability density function little g of v, which is given here. And the first thing we've got to do is we've got to obtain the cumulative distribution function for v, and then we've got to use that to deduce the interquartile range for v. Well, first of all, if little v is less than 32, then g of v, big G of v, the distribution function for v, is the probability that the average speed is less than v, which is smaller than 32, but we know from the probability density function that the possible average speeds for the lorry lie between 32 and 96. So there's no possibility at all that the average speed is less than 32. So we know that if little v is less than 32, g of v must be equal to 0. If v lies between 32 and 96, then we have that g of v is the probability that the average speed is less than or equal to little v. So that's going to be the integral between 32 and little v of the probability density function, which is 1 over 4096 times v. Doing the integration, we get 1 over 8192 times v squared. Put the limits of v and 32 in, we get g of little v is v squared over 8192, take away 32 squared over 8192, which turns out to be 1/8. And then, if little v is bigger than 96, then we know that the probability that the average speed is less than or equal to little v must be 1, because we know all the possible average speeds are less than 96. Now that we have got the continuous distribution function for v, we can find the interquartile range for the average speed. So let's use the symbol v subscript L for the lower quartile. Then we know that the value of the distribution function at the lower quartile must be 0.25. So we've got the lower quartile squared divided by 8192, take away an eighth, must equal 0.25. or the lower quartile squared divided by 8,192 must be 0.375. Multiply up by 8,192 and square root, we get the lower quartile is 3,072. Repeating this argument for the upper quartile, we know that the value of the distribution function for the upper quartile must be 0.75. So that gives me the upper quartile squared over 8,192, take away an eighth, must be 0.75, which ultimately gives me the upper quartile being the square root of 7,168. So the interquartile range is the upper quartile minus the lower quartile, so that's the square root of 7,168, take away the square root of 3,072, which gives us an answer of roughly 29.2 kilometers per hour. And the final part of this question asks us to give a reason why the function f, so the probability density function that we had at the beginning of the question, might not be a realistic probability density function for the time taken to travel that 96 kilometers. There might be lots of reasons you might be able to think of, but an obvious one is that this model gives a maximum possible time of 3 hours for the journey. And if there was a serious accident on the motorway, then it's quite possible that delays might result in a journey that was much longer than just 3 hours. Our final example is an amended question from the 2013 S2. We're told the radius of a circle is a continuous random variable that is uniformly distributed on the interval 6 to 8. And we've got C denotes the circumference of the circle. We have to determine the mean and variance of C and the probability that C is less than or equal to 45 to start with. So let's start with what we know about the radius of the circle. We know that the radius of the circle is uniformly distributed between 6 and 8. So that means the value of the probability density function is constant, and that constant must be equal to a half, so that we've got an area underneath the PDF of a half times 2, which is 1. And we know that the area under the PDF has always got to equal 1. If we use the formula booklet, we know that the expected value of R is going to be 7. We could have got that using symmetry as well. The formula booklet will certainly tell us that the variance of R is 1/12 of 8 minus 6 squared. So that is 1/3. Now we know that the circumference of the circle is 2 pi r. So the mean, or the expected value of the circumference, is going to be the expected value of 2 pi r, which is the same thing as 2 pi times the expected value of r. So that's 2 pi times by 7, which gives us 14 pi. The variance of the variance of C is the variance of 2 pi times r, and that is 2 pi squared times by the variance of r. So that gives me 4 pi squared times by 1/3. So the variance of C is 4 pi squared divided by 3. The probability that C is less than or equal to 45 is the probability that 2 pi r is less than or equal to 45. So that's the probability that r is less than or equal to 45 over 2 pi. Or in other words, the probability that r is less than or equal to 7.162. Now, the probability that r is less than or equal to 7.162 is the area on the graph, underneath the graph, to the left of 7.162, because areas under a probability density function give us probabilities. That area is going to be a half, that's the height, times by the base of that shaded region, which is 1.0162. So the area there we've got is a half times 1.162, which is 0.581. And that is our probability. The second part of the question says we've got A denoting the area. We've got to determine, first of all, the probability that A is bigger than 150. Well, we know that A is pi r squared, so we're looking for the probability that pi r squared is greater than or equal to 150. In other words, the probability that r is greater than 150 divided by pi, or the probability that r is greater than or equal to 6.9099. So back to our diagram again. That's the probability r is greater than or equal to 6.9099 is the area underneath the probability density function to the right of 6.9099. So that is a little rectangle. The shaded region is a little rectangle whose height is 0.5 and whose base has got size 1.0901. So the area is 0.545. So that's my probability that the area is greater than or equal to 150. Now I've got to find the mean and the variance of A. Well, the expected value of A is the expected value of pi r squared. Pi is a constant, so we can certainly say that's just the same thing as pi times the expected value of r squared. But remember, we know that the variance of r is 1/3, and the variance of r is the expected value of r squared, take away the mean of r squared. So we've got 1/3 is the expected value of r squared, take away 7 squared. Of course, we've already found out the mean of r, the expected value of r is 7. So we've got the expected value of r squared is 49 1/3, which is 148 divided by 3. So the expected value of A is pi times the expected value of r squared, so that's 148 pi divided by 3. For the variance of A, well, we need to remember that the variance of A is the expected value of A squared minus the expected value of A all squared. So that's the expected value of pi r squared itself squared minus the expected value of A squared. We know that the expected value of A is 148 pi over 3. We also know that pi r squared squared is pi squared r to the 4. Pi squared is a constant, so we can pull that out. So we've got pi squared times the expected value of r to the 4 minus 148 pi over 3 squared. So we've got to work out the expected value of r to the 4. Well, the expected value of r to the 4 is just going to be the integral of r to the 4 times by the probability density function. So that's the integral between 6 and 8 of r to the 4 times by a half. So the integration gives us 1/10 r to the 5. And when we put the limits in, we end up with 12,496 divided by 5. So we're going to have, for our answer to the variance of A, 12,496 over 5 times pi squared. Take away the square of 148 pi over 3, which is 21,904 over 9 pi squared, and that tidies up to 2,944 over 45 pi squared.